Hey, we have a test tomorrow over expression. So one of the things we learned on page 23 is we learned 5 properties that tell us if two expressions are equivalent. So remember that the associative property has to do with parentheses, and it means that the parentheses can move. So the order of the numbers won't change, but the parentheses can move. And so if you notice on this one down here, they've moved the parentheses from being around the 3 and the 5 to being around the 2 and the 3, but the order didn't change. So this one right here is the associative property. Commutative starts with CO. You can remember that that tells us we can change the order of the numbers or variables, whatever it is. So if you notice this one up here, the only thing that has changed is they're in a different order. So that's commutative. The inverse property can be about adding two opposites and that being equal to 0, but I don't see anything about that. It can also be about multiplying a number times its reciprocal. And so when you see 4 is the same as 4 over 1. And so if you flip that to its reciprocal, that's 1/4. And if we multiply that out, it equals 4/4, which is 1 whole. And so that one is the inverse property. The identity property is where the number stays the same. It keeps its identity. So when we add 0 to a number or we multiply by 1, the number is going to stay exactly the same. So that's the identity property. And then the distributive property, remember that that has two operations in one. It's always going to have parentheses with a number on the outside of the parentheses and some addition or subtraction on the inside. So two operations in one problem. And we can do hippity-hoppity distributive property. 7 times W is 7W. 7 times 12 is 84. So this one right here is the distributive property. Okay, so we do need to be able to evaluate expressions. There's some exponents here, and so that's found on page 20. And then both of them do need to follow the order of operations, which you can find on page 22. So here we do have some grouping symbols. Make sure that if there's negatives in your problem that you are using your integer rules. So for division, that would mean using a Dorito man. So a negative divided by a positive is going to come out to a negative answer, and that would be -3. We're done with the grouping symbols, and I know that we do have some parentheses over here, but those don't count as grouping symbols because they only have numbers on the inside, not an actual problem. We don't have any exponents on this problem. We don't have any division, but we do have multiplication, so we would work that next. And again, we do need a Dorito man, since it's got a negative in it. A positive times a negative is going to come out to a negative answer. So that's going to be -20. And then all we have left is addition. But again, these are negatives, so we have to ask ourselves if they have same signs or different signs. And in this case, they have the same sign. So we find the sum and we keep the same sign. So -23 for that one. The next one does not have any grouping symbols. Again, yes, we see some parentheses there, but they only have a number on the inside. They don't have an actual problem. So this would count as our exponents step. And remember, I always want you to write out exponents in expanded form. So -3 times -3 times -3. So using our integer rules, a Dorito man is going to tell us that a negative times a negative is going to be a positive. So 3 times 3 is 9, and it's going to be positive since they were both negative. So that's 9. Then we have to do 9 times -3. So that takes another Dorito man. 9 is positive, the 3 is negative. So that's going to end up coming out to negative, and 9 times 3 is 27. And again, exponents are on page 20 if you need to go back and refresh your memory on those. And then we don't have any multiplication or division here. We only have the addition, but again, we're dealing with negatives, so we have to ask ourselves, is it same signs or different signs? And in this case, it's different signs because we have a positive and a negative. Different signs, we find the difference, which is 20, and we have more negatives, so -20 for that problem. So in this one, they're saying which expression is equivalent to m times 32. So sometimes we can use our properties to help us with this, but another strategy we learned on page 26 is that we can substitute the number 2 everywhere where we see an m, and then using the order of operations, we can work those out and see which one gives us the same thing. So 2 times 32 is going to give us 64. So that's the number that we're looking for. If I do what's in the parentheses here, the 2 times 30 is going to give me 60, and then 60 plus 2 is 62, which is close, but it's not the number we were looking for. On this one, we've got 2 times 30, which is 60, but then we have times 2, which that's going to give us 120. That's too big. Here we have the 2 times 30, which is the 60, and then 2 times 2, which is 4. 60 plus 4 is 64, so that looks good. But we always want to double check by testing all of them. So 2 times 3 is 6. 6 plus 2 is 8. And nope, that's not even close. So the only one that came out equivalent was C. Next question is about prime factorization. That was before fall break, so you may need to go give yourself a refresher, watch my video, look at your notes. But remember that the strategy we learned is called upside down division, and since it's prime factorization, we need to make sure we're always dividing by prime numbers like 2, 3, 5, 7, 11, and so on. If it's an even number ending in 2, 4, 6, 8, or 0, I like to usually start by cutting it in half. So we know we can cut 180 in half. Think about 18. Half of 18 is 9, so half of 180 is going to be 90. Be careful here because sometimes people want to divide by 9 or by 10, but those aren't prime. So I would think about either cutting it in half again, or maybe dividing by 5 since it ends in 0, or I know that I can divide that by 3, and that's going to give me 30. I could also divide 30 by 3, which is going to give me 10. 10 is divisible by 5, which goes in 2 times. 2 is divisible by 2, which gives us our 1 and means we're done dividing. You could have gone in a different order than that, but regardless of what order you go in, you should end up with the same prime factors along the side. Remember that you have to put them in order from least to greatest and in exponential form. So I like to do that in 2 different steps. So least to greatest would be the 2's, and then we've got a couple of 3's, and then our biggest one is 5. But remember that when you have multiples, you can put them in exponential form. So that would be 2 to the second power times 3 to the second power times 5. Okay, when we flip to the back, we've got a couple of order of operations problems here. Hopefully we have enough room for this first one. They didn't give us a lot of room, but we do need to make sure that we're using GEMDAS for both of these. Right here, we do have some grouping symbols, so we're going to start there. 12 minus 4 is going to give me 8. I'm going to bring down everything else exactly the same, being sure not to make any mistakes on copying that stuff down. Then we do have exponent. 2 to the second power is going to be 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 gives me 16. Everything else is staying the same. We're done with our exponents. We do have multiplication and division. Remember that we work those left to right. So I started with my division because it was on the left. And I did think I was going to run out of room here, so we'll just make the best of this. 8 times 4 is going to give me 32. And then we add and subtract from left to right. So we're going to do the subtraction. I'll just move over here. That's going to give me 8. And then 8 plus 32 is going to give me 40 for that first one. And for the second one, we should also be using GEMDAS. And again, we also have some parentheses here. So starting with our grouping symbols, 4 plus 9 gives me 13. Everything else is going to stay the same. We do have exponents. 6 to the second power is 6 times 6, which is 36. And then we've got multiplication. We've actually got two different sets of multiplication, but we go left to right. So 7 times 13. I don't know that, so I'm going to work that out to the side. That's going to give me 91. I also don't know what 5 times 36 is, so I'm also going to work that out to the side. That's going to give me 180. And then we can do that subtraction. Notice, though, that we have a smaller number minus a bigger number. So I know whatever it is, my answer is going to come out to be a negative number. Okay, so I ended up with, oh, this should have been 7. I ended up with 89. And because it's negative, or because we knew it was negative, so negative 89. Okay, moving on to number 6, which is not an example of prime factorization and why. So it comes down to the name, prime factorization. Prime factorization has to be all prime numbers. 3, 5, and 11 are all prime. 7, 3, and 13 are all prime. 5 and 7 are prime. 2 is prime, 3 is prime, but 9 is not prime. So I would say D is not an example of prime factorization because 9 is not prime. 9 is divisible by 1, 3, and 9. So it has too many factors to be a prime number. Okay, on this next one, we are looking for expressions. This is on page 24, expressions versus equations. So remember that an equation is going to have an equal sign or the word is and then the number. So that means this is an equation, it's not an expression. This has the word is 16, so that's an equation. This does not give us the answer, so that's an expression. This doesn't give us the answer, it's not an expression. This doesn't give us the answer. Sorry, it is an expression. These are expressions. This doesn't give us the answer. It's an expression. This one does give us the answer, so that's an equation. And this one is also an equation because it says the answer is 2, right? So is 2 means equals 2, and is 16 means equals 16. So that's how you know that those are equations. Last but not least, we're going to evaluate these two expressions to see which value makes them equivalent. So remember, that just means you try out all of these. So I'm going to try out with, if n is 1, that's going to be 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7, 8, 9. 7 does not equal 9. And it says right here they're supposed to be equal. So we know that's not our answer. We can try 2. If n is 2, that's going to be 2, 4, 6, 8, 9, 10, 11 on the left-hand side. And then 2, 4, 5, 2, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that looks good, but we're not sure yet. So let's look at our other answer choices just to make sure. If n is 3, that's 3, 6, 9, 12, 13, 14, 15. 3, 6, 7, 8, 9, 10, 11, 12, 13. 15 and 13 are not equal, so no, that's not my answer. And then the last one says that n equals 4. So if all of these were 4s, let's see what would happen. 4, 8, 12, 16, 17, 18, 19 on the left-hand side. 4, 8, 9, 10, 11, 12, 13, 14, 15 on this side. And 19 and 15 are not equal. So the only one that gave us two equivalent expressions was answer choice